Hi. I'm a geologist by training originally, so it's always nice to come to meetings like this. So I was asked by Nina very broadly to provide general background on fire ecology because she feels like debris flow scientists don't know quite enough about it. Forgive me, I don't know if that's the case. Hopefully I'm going to hit some kind of mark, and I'm right before lunch, right? So anyway, people will probably start leaving early if I'm not really hitting the mark, but maybe I'll leave you hungry for more. Anyway, so I'm going to go through some definitions, and then I'm going to dive into stuff that's maybe a little more apropos. You can fall asleep if you know all this stuff, but I thought I should tell you what this is, right? So fire ecology, what is it? Well, it's the study of the role that fire plays in ecosystems. Ecology, of course, comes from Greek, oikos and logos. This is the study of our home, right? We're talking about the economy of the planet, the economics of nature, if you will. Study of living things, their environment, and how those things interact, all right? So essentially, ecology covers nearly everything that happens on the planet. And an ecosystem is a community of interacting organisms combined with their environment and their interactions. So it includes everything from predators, all of the biotic sides of things and the different guilds that are there along with the physical environment as well. Is there a timer on here? Yeah, I see it. Okay. So, all right, again, you guys deal with disturbance, with debris flows. That's a kind of disturbance, right? Essentially, and when you talk about these things over large spatial scales, and long periods of time, you usually talk about regimes. How do things tend to function in a landscape? So an ecological disturbance is, I'm going to read this, any relatively discrete event in time that disrupts ecosystems, community or population structure, and changes resource availability and or the physical environment. That's from the classic book by Pickett and White from '85 that covered natural disturbances and patch dynamics. But someone like Philip Grime would say it's also really important to understand that it's a disturbance when it removes or kills biomass, all right? Otherwise, we'll probably call it a stress on the system, all right? So fire can kill organisms, it can induce or reduce reproduction, it changes movement and migration patterns, therefore it affects populations in a lot of different ways. It can change ecosystem structure. In some cases, it can maintain ecosystem structure, and we'll be talking a little bit about that later on. It certainly alters availability of resources, and obviously it can lead to erosion and soil loss. And of course, it also interacts with other ecological disturbances, and you all work with one of those. And this is just an example of other kinds of ecological disturbances that all have their own regimes. One of the things I want you to understand, if you don't already, that fire is quite a unique ecological disturbance. It's basically an herbivore. The way that it works on landscapes, right? So like herbivory, it requires some kind of fuel to actually occur, but fire is a little bit less selective, or in some cases much less selective, depending on what kind of herbivory you're talking about. And by consuming fuel, the occurrence of a fire greatly changes the probability of a recurrent fire, and it also likely is going to change the behavior of a subsequent fire as well. And that makes it quite unique, a little bit like the way herbivory does as well. So the characteristics of fire depend on the growth rate of the fuel it consumes and frequency and the intensity and the severity, which again, I'll talk about the difference between intensity and severity here. They're inversely related as a result. The more frequently you have a fire in the system, the less time there is to build fuel. Therefore, there's a major impact on subsequent fire, okay? All right. Oh, and then, yeah, just to note, because this thing is really dark. I almost feel like I should wear my glasses. But anyway, these other things that I've noted, they're a little more allochthonous, right? They're sort of outside of the ecosystem. They are visited on landscapes. They're visited on ecosystems. And therefore, their occurrence doesn't depend on the condition, the state of the ecosystem. Certainly, their effects depend on that, but not the actual occurrence. But fire, it does very much. Okay, usually in a room where people are starting to fall asleep and you're not there yet, I would probably ask you to fill this out for me, but I'll save a minute or two by not doing that. So fire occurs where you've got oxygen, where you have fuel, and where you have an ignition source, and then the ability to actually continue that heat source because you need that activation energy. And I'll show the combustion equation here in just a second. Little tidbit about oxygen. Right now, the Earth's atmosphere holds about 21% oxygen. It's kind of hard to believe that 99% of the atmosphere is two elements, right? Nitrogen and oxygen, and carbon is 0.04%. Yeah, that's what's driving everything that's going on right now, right? If you get down to 15% oxygen, you really can't burn stuff. If you get to 35% oxygen, you can't stop stuff from burning. So there's a pretty narrow range, right? From spontaneous combustion to you can't burn things. So here's the combustion equation. I'll just note one of the interesting tidbits about fire itself is that you're actually generally not burning the substrate itself, but rather what happens is the activation energy is required to release gases like methane or octane from the burning substrate, and that is actually what burns. And so, like if you're familiar with forest fires, you can walk around and you realize that actually a typical, even a very high intensity fire is only removing in situ maybe 20% of the carbon on site, because it's burning the surface mostly of the things that are burning rather than the interior. So once you have a fire, I don't know what it is, by the way, fire people in triangles. There's a lot of triangles in fire. I don't understand that. We had a lot of those in geology too, and then people realized, I think we need more than 3 factors to drive everything. Fire hasn't really gotten there yet. Hope no one in here works in fire. I do, I guess. But anyway, in terms of the fire behavior triangle, so you've got a fire, it's moving on the landscape, and what is going to drive the way that the fire behaves on the landscape? And that's probably more important to the kind of things you talk about. Fuel, again, is here. Weather, obviously, is a major driver of the way fires, their comportment, the way they behave, and obviously topography. And then here are just some examples of some of those things. I mean, obviously, those are really big terms, and they cover a lot of stuff. I work a lot with fuel availability. Why? Because I've been working with managers. I worked in the Forest Service for more than 2 decades. And that's the only thing of these that we can really change. I mean, obviously we're changing the climate, but that's a little bit of a different question, right? But we can change fuel on landscapes. Okay, so every ecosystem has a different relationship with fire. Some people sometimes use this concept of, they say, oh, that plant's fire adapted. That's a dumb way of thinking about it. Actually, organisms are adapted to a certain regime of disturbance. Basically, through the life, the span of the existence of a species, which could be anywhere from a few 100,000 to a few million years, or in some cases much longer, they will see fire. It will happen. But they may not be very well adapted to having fire be more often than about every 1,000 years or something. Okay? So when you talk about disturbance regimes, organisms are adapted to certain regimes of disturbance. It's not that they're just adapted to a given, at least that's not a good way to refer to it, I don't think. Anyway, so this general relationship, right, it doesn't define a certain or a single event. You'll always have outliers, all right? And that's where detractors always have fun writing response papers or litigating and stuff, because they're always trying to refer to the outliers of the regime. And these are some of the things that we characterize regimes by. You guys all know this. You would say the same thing about debris flows. What's the characteristic frequency or the intensity or the severity or the patchiness or the shape, or what sets it off, or what season does it tend to happen? And for debris flows in fire, that's going to change depending on where you are, right, in the landscape, very, very much. So we can map and categorize fire regimes just like you can do that for any other disturbance. Now, in fire ecology, we usually use 2 factors to do that. It's really rare to see classifications based on other factors. It's almost always frequency versus intensity or severity. And again, I'm going to get into this intensity-severity thing. Why? Because they're impactful. We know they have impacts, and we've been able to measure them. They're easy to understand. We can map them as well, and they're actually inversely related. So they tend to create really easy to interpret XY graphics. The example that I've given here is the land fire regime classification. That's probably the one that's most used in the United States, because it is attached to the updated fuelscapes that are provided to fire managers and forest managers across the US well, they're actually only updated about every couple of years, although that's going to become an annual thing here really soon. And let's see, I just want to note that I'm going to be talking about fire regime groups N1 and 4 a lot later in the presentation. These are characterized by fire frequency and by dominant fire severity. Group 1 is essentially your oak systems, open pine forest, mixed conifer forests, where fire was very, very frequent historically. And because it was very frequent, the severity tended to be quite low. All right. Fire regime 4 is quite different. This is characterized by things like chaparral, coastal sage scrub, and a lot of subalpine forest systems, also some wet forest systems, where fire frequency might have been what they call moderate, between 35 and, oh sorry, that's a fire return interval, and I'll explain the difference between those two in a second. But maybe between 35 to 200 years between fire, but when they burn, it's generally hot. Why? Because you're giving that ecosystem a lot of time to build a lot of fuel into the system. A great example of this would be a lot of lodgepole pine forests, for example, as well, in the Rocky Mountains. And I said they could be mapped, and this is the land fire regime map. Note a couple of things about this. One is that this is characterizing hypothetical fire regimes before Euro-American settlement on the landscape. So it necessarily incorporates indigenous burning, which we have a lot of trouble disaggregating from paleoecological data from the lightning, but really based on where lightning is really prevalent and where it's not, and where there still is a lot of fire, you get a good feeling for the impact of anthropogenic burning. And where you mostly see that, big differences along the west coast of the US, where there's very little lightning, but there is an incredible amount of fire in the paleoecological data. And also, I'll just note that these aren't perfect, like most maps. We just heard about some inconsistencies in radar data. Well, believe you, trying to map historical fire regimes has a lot of inconsistencies. And so I tried with some colleagues to build a little bit more consistent map of fire regimes in California, but whatever, there are a lot of different versions of those out there. All right, so how does fire impact erosional processes? Okay, I'm guessing that you guys could probably recite this stuff with your eyes closed. But obviously, fire is a major driver of erosion on landscapes, and the impacts can be direct, they can be indirect as well. And as I noted before, I'll just note that we best understand the impacts of fire frequency and fire intensity / severity, because this is what people have studied. They seem to be very impactful, etc. So fire frequency. So we call it fire frequency, but that's usually not what we're measuring. We're usually using its inverse, which is called fire return interval, right? So the number of years between an event. It's just a little bit easier to understand. Fire return intervals in fire regimes can go anywhere from a year to 1,000 years. There are a lot of grassland systems that are being literally burned every year, sometimes multiple times in a year. And there are plenty of forest systems in very wet and cold places where it's extremely rare that you would ever see a fire in the system. Major changes to fire frequency can have pretty important impacts on erosional processes, but that's usually due to indirect effects, like the effects that having too much fire might have on the ability of vegetation to reoccupy a site, for example. Probably more important is fire intensity and or severity, depending on how you measure it and how you would use it. But intensity is just a measure of the thermal energy released, right? So we actually don't usually have really good measures of this. You have to have thermocouples. Now, of course, we've got satellites that can do this for us to an extent too. Typically, it's measured in kilowatts per meter, which seems kind of weird, but it's measured linearly in the flaming front of a fire. The thing about a fire, and I guess any disturbance is, I think about the way a debris flow works, right? The head of the debris flow is really different than the end of it in terms of the impact it's going to have on a channel, right? So you see that with fires too. The flaming front is where most of the active burning is happening. There can be long duration smoldering after that, and those are going to have different impacts. So severity is a measure of the impact of fire intensity. We often use it as a surrogate, it just sort of, uncarefully. Very, very often, but you have to be a little careful with it. There is a correlation. They seem to work relatively well, but it's not just a function of intensity, but also the duration of burning that happens on the landscape, and the characteristics of the fuel have a lot to do with how the intensity of a fire evokes the severity on the landscape. Like, are you burning deciduous trees or conifer trees? Did they have the leaves on the tree or not? Was the tree under water stress? Did the tree hold a lot of dead material in it? Was it a shrub? Was it a tree, etc.? And the fuel characteristics also depend on things that drive productivity, right? And fuel moisture. So you can imagine topography, slope aspect, rainfall, things like that as well. You can measure soil burn severity in a bunch of different ways, and the two I'll focus on are something that we always have issues with in the Forest Service, not just with respect to people on the ground understanding the difference, but with both supporters and detractors understanding the difference. I got involved in this early on when I joined the Forest Service in the early 2000s, because it's common for litigants to use the soil burn severity map to talk about vegetation burn severity, because the soil burn severity map will always suggest that the high severity proportion of a fire was maybe 10%, whereas the vegetation burn will say it's 50, and they will grab the soil burn and use it in court to suggest that we are overestimating the amount of burning and we shouldn't be doing anything about it. Anyway, I got pulled into this since I worked for a federal agency. Soil burn severity, obviously, as you know, this is bear team stuff, right? This is assessing burning conditions and what impact do they have on things like flooding and erosion, right? Whereas vegetation burn severity, it's basically the same thing. You're looking at biomass impacts, okay? Might be measured, if you're talking about field studies, you're usually doing, individual specific measures. Like, I run the California Prescribed Fire Monitoring Program, and we are always out measuring, how much scorch and how much torch and how high is the char on the tree bowl, and how much biomass was burned off the end of a stem on individual organisms. In remote sensing, it'll be something that's looking at that across forest stands. So these are just some pictorial examples of a paper I had to write in 2008, responding to some nonsense that was written in the literature. And I tell you, that was one of the things I was so glad. I retired from the Forest Service at the end of 21, and I was just so glad to get that part out of my life, just having to respond to absolute nonsense and lawsuits all the time. Top left is the standard vegetation burn severity output. Like the monitoring trends and burn severity produces that, those maps. There's some issues with MTBS data though, and if you want to use those data, ask me about them, because you can't really use them in bulk or in temporal sequences, and I'll tell you why. I won't do that here. But what this is this relativizing the severity measure so that you actually, what the black is representing is places where you've had basically stand replacing fire and where more or less all the trees in this case are dead, okay? It is relativizing it because it's saying, I don't care whether there was 30% cover early or 70, I want to know whether all the trees died, all right? If you get to the second line, you get to the bark map, which is the burned area reflectance classification. That's the map that gets delivered to the BEAR teams for the soil burn assessments, right? And that does a much better job of assessing intensity, because it doesn't relativize and it takes into account the actual biomass ahead of time. And then the bottom left is the actual, as a standard final soil burn severity map that comes after field visits, incorporating soil, information, et cetera. And what you see is that the correlation between the low severity and moderate severity is pretty good across those three, but it's quite different in the high severity. You can see there's a lot of high severity in the top left and very little in the bottom. And then just maybe, in a couple of photos, the same example of the same issue. These are places, the top one is the Story fire, the bottom one is the McNally fire. In both places, there was essentially complete stand mortality in the trees. However, one of those was mapped as low severity in the soil burn map, and the other one was mapped as moderate severity. Why? Low slopes, soil type, litter cast onto the ground, all sorts of other things that mitigate the impact of rain splash and minimize overland flow and things like that. Okay, so in terms of direct impacts of fire on erosional processes, this is mostly driven by heating and burning, right? And the impacts are pretty much immediate. So rock spalling, as a geologist, that's always fascinated me. Anytime you go into an intense fire, there's rock spalling everywhere. And that paper by Buckman et al. In Nature Comms in 2021 is really cool because they turned it into a regional and global assessment, and it turns out rock spalling is hugely important to soil creation and weathering on large landscapes. I saw this woman give a talk in Australia a couple weeks ago, and it was really interesting to talk with her. Obviously, it removes vegetation and litter. You change soil microbiology, soil fauna, right, and their activity rates. Those change a lot. Soil structure changes, hydrological. Obviously, probably a lot about hydrophobicity. A lot of this is driven by intense soil heating, but not too intense or not, tense enough. You lose organic matter. You're obviously going to destroy soil aggregates and a lot of different kinds of soil as well. So you can also have indirect impacts. Most of these are post-fire. They don't happen immediately as a result of the fire, and they tend to have a little bit of a duration. They might be a year, it might be 2 years, some cases 3 years. And so here you're talking about changes to things like infiltration. Overland flow obviously is greatly increased in severely burned places, or in a lot of them anyway, for quite a while, a couple of years maybe after a fire. But at a more broader scale, you can have major changes to discharge, to peak flows. Channels are obviously going to change. We saw some great examples of changed channels earlier today. You enhance soil erosion, you increase soil detachment, right? Redistribute soil all over the place. And then more apropos to what we're talking about here is that you're going to increase the way, just sort of redistribution of soils and regolith across landscapes by mass movement. And obviously debris flows is one of those things. Okay, so in terms of debris flows and fire, how am I doing here? Is that right? How far in am I? I got 10 minutes left? 12. Okay, cool, thanks. Okay, oh yeah, I got 30. I'm used to 20-minute talk. No, I got 12 until I'm done with my 20. Okay, whatever. I talk fast anyway, I'll just go faster. No, I won't. I'll just finish early then. Anyway, everyone knows that kind of these background conditions favoring debris flows, steep slopes, certain kinds of morphometry, right, of slopes, weak, loose rock and soil, heavy rainfall. But if a site's reasonably vegetated, even when you have these things, debris flows in most landscapes are relatively infrequent, right? So fire plays kind of a gate function, right? It's opening the door to things that don't tend to happen if you have decent vegetation, particularly woody vegetation maybe with broad leaves. And I'll just note, I wanted to spend more time on this, but this is just, the science background table or sheet from the USGS landslide hazards program, right, where they're using the logistic regression to kind of, remember when they have a fire, there's kind of a real quick prediction of the probability of debris flows on landscapes. We use this a lot in the Forest Service. And what you'll notice is if you look at the equation for the X term in the logistic regression, every single one of those terms is driven by some fire-related thing, right? You've got the bark map. For the first one, you have the unrelativized veg burn severity map for the second, and the KF factor, that's the fine, this is erodibility, right? The fine soil fraction less than sand size. All of that's driven by whether fire is removing biomass, wiping out soil aggregates, and removing litter and biomass from the cover, right? So fire is driving all this stuff. Now, what's kind of interesting is that fire regimes are changing. Now, obviously, they're always changing. I mean, you guys have backgrounds in geology. The world is not static, and it is constantly changing, and we get that. But they're changing really, really quickly, driven largely by human agency. This was a publication from the Nature Conservancy in 2007 that actually got quite a lot of press because they split the world's ecosystems into, what do they call them? Fire-dependent ecosystems, fire-sensitive ecosystems, and fire-independent ecosystems. And they showed that something like 55% of the Earth's surface has, ecosystems in which fire is a pretty important part of sort of ecological processes. But they also showed that more than 3/4 of the planet was seeing rapidly changing fire regimes, obviously due to human impacts on the landscape. And you can map it at finer scales. We've mapped it in California. About 15 years ago, we built this thing called the Fire Return Interval Departure Geodatabase. This is re-upped every year by the Forest Service and CAL FIRE, by their FRAP program. And essentially what we're doing is we're mapping current fire frequencies versus putative pre-Euro-American settlement frequencies from paleoecological data. And I'm not objective, but I think it's a pretty cool tool. It gets used a lot in the Forest Service. This one, by the way, has been generalized to the ecological subsection boundaries, so it looks a lot prettier. It's normally a pixelated kind of thing that the colors don't show up quite so well on. But what this shows really clearly is that in these fire regime group 1 forests, remember, very frequent fires, low severity, oak forests, pine forests, mixed conifer. In Northern California and then in the little forested islands in Southern California, what's the issue here? The issue is way too little fire. These are systems that saw fires every 2, 3, 5, maybe 10 years. Most of that landscape hasn't had a single fire in 120 plus years. Okay, even with all the fire that we've had recently on the landscape. In Southern and coastal California, the situation's a little bit different. These are places dominated by chaparral, sage scrub, etc. And in these places, actually, the big issue is too much fire to maintain chaparral in the landscape. Now, I'm not going to dive into the history of indigenous burning in this landscape, but if you want to talk about that over lunch, maybe you could buy me a cocktail or something. I will go on and on and on and on. But I won't do that right now. Anyway, it gives you a good idea of how different. So this idea that, and this kills politicians because we finally got them to a spot where they understood, oh, fire suppression, wow, yeah, that's really got to deal with all the fuels from that. And then they try applying that model to Southern California. It's a really bad idea because it's exactly the reverse of the problem there. We can also look at human changes to forest fire severity. In this particular case, I've done a lot of work in northern Baja California because the North American Mediterranean climate zone goes about 1/3 of the way into Baja California. And if you're looking for an interesting place to go, just for a geo or a botany or an ecology field trip, go to the Sierra de San Pedro Martir, which is an exact ringer for the east shore of Lake Tahoe. Same soils, same species, same substrate, same climate. And it's about 2,000 feet higher down there, and that almost exactly compensates for the latitudinal difference. It's amazing. You can stand in that system, and there's no big lake below you, and that's the only difference. The other big difference is that, I just said that was the only difference. An important difference is that it was not logged. The east shore of Lake Tahoe was cut down to every last tree. Looked like the East Bay. Right in the 1880s. Everything got cut down. All the big trees are gone, and it's been under fire suppression for 120 years. And in Mexico, they only started that in the 80s and early 90s. So we use this forest as a reference system for understanding how fire and ecosystem processes work. And so what you'll see is these little circles I drew. That's the fire severity spectrum for all the fires that we were able to get RD and BR measurements from Landsat for about a 20 or 30 year period. Look how small that little high severity block is in there. These fires are burning at 3 to 4% high severity. You're rarely ever killing canopy trees in these fires. And look what goes on in the Sierra Nevada over the same period of time. Basically, we're losing 30 to 50%, and it's much worse today, but you're losing 30 to 50% of your tree biomass in a lot of the Sierra Nevada fires today. So, okay, so how will these changing fire regimes impact debris flow regimes? I'll cover that now in a second, but I want you to remember that it's basically due to this dependency between fire frequency and severity and how vegetation is affected by that. That's sort of the operational term in this equation. And then I'm going to talk about fire regime groups 1 and 4. So top left is the way that your standard mixed conifer forest ought to look if it's functioning normally. Relatively low cover, dominated by big trees, mostly fire-tolerant groups like pine and oak. Very low fuel loading, but very heterogeneous. Lots of understory species, had a lot of fire. Today, in California, it tends to look more like that thing in the bottom right. All right, when you put fires out for 120 years, that's what the system starts to look like, okay? It's a jungle of live and dead fuels. It's dominated by fire-intolerant species, all right, that don't survive fire, but also propagate it more, a little more easily because they have, if you look at the trees there, the big difference in the ones on the left is there are no lower branches on the pines. The fire-adapted, I use that term, I told you shouldn't do it, but fire-adapted pine species will drop their lower branches. They do it so that ground fire doesn't get into the canopy. Look at the firs in the bottom right picture. They don't have that adaptation, so they act like candles. Once you get fire into that system, the fuels hits the canopy immediately and you're going to kill the canopy trees. Anyway, it's a really, really different forest with very, very different impacts. And fire suppression's had a major impact on this. So Angora fire, which was just across the way here, in 2007, in which I did a lot of work in because I lived just outside of the perimeter of the Angora fire, so I could drink my tea in the morning and march right into the fire and work and walk back for lunch and then come walk. It was great. I mean, I was incredibly productive that summer. And you can see the difference. So bottom left is the way a lot of that forest looked, but they had done restoration in probably 15%. Actually, it was fuel reduction, but they happened to be parallel concepts in fire regime group 1. And when the fire hit these places, look how different the impacts were. Almost no mortality in the places that had been restored from this fire. And also protected hundreds of homes, saved a lot of lives probably. Whereas the forest that looks like your standard Sierra forest today, nearly complete mortality on most of the landscape. And look at the impacts to soil, to streams, to carbon, and all that kind of stuff as well. So then when we talk about chaparral, it's a little bit of a different situation. Top left picture is your standard healthy chaparral site. This is not a place to build homes. Please don't. Oh, too late. I've only built about 10 million homes in this system already. But basically, you're talking about really dense 6 to 8 foot tall shrubs that you would never go into unless you were forced to. I don't think I'd even do it if I were forced to. That's really close canopy, high fuel loading, lots of aromatic fuels that just burn explosively when you can get them to actually burn. Nothing going on in the understory until you burn it, and then there is this miracle of dozens to hundreds of species which just come out of the ground because they've been sitting there for 60 years waiting for the fire signal that they need to crack their seed coat so they can come out, all right? So that system actually did not burn very frequently historically because there's no lightning ignition system here. Before American Indians showed up, probably almost never burned, okay? Really interesting long-term dynamic between chaparral and human impacts on the landscape. But anyway, today, the system looks more like the picture on the bottom right, where you have this patchwork of places where it's just simply burning too often to maintain woody biomass anymore. It's getting filled up with exotic grasses. Fires are actually becoming less severe in chaparral because there's a lot of openness in the system now, but it's flashier and it's a lot easier to get it ignited, actually. Anyway, pretty different systems. And then if you take this, forgive me, I can't remember the year of this. This is probably 5, 6 years ago. But I mean, look at the Angeles National Forest. I mean, that's about, what, 700,000 acres or 800,000, the whole picture. Look how much of that landscape has burned in the last 0 to 10 years in this picture. Pretty extraordinary. All right, so in terms of summary of fire regime changes, I'm going to just summarize 2 things out of this. Fire regime group 1 in your classic Western conifer systems, very frequent fire historically, maybe a range of like 5 to 50 years typically. Jump over 2 columns and you see that in California, today the average is about 85 years. The mean min about 55, mean max obviously is at the limit of where our data go. But a lot of places are burning, we have places now that are burning 20 or 30 or 40 years, and you're going to lose forest in those sites probably because it's so full of fuels these days. But then if you look at the chaparral system, it's the reverse. Used to burn relatively infrequently. Today, the fire return interval is actually shorter, and there are a lot of places in the state where there are fires happening every couple of years. Along major freeway systems, you can't even really call it a shrubland anymore. There are some shrubs in the system, but it's basically almost entirely Mediterranean basin, Eurasian, Central Asian, Southern European invasive species. And then in terms of severity, again, it's the reverse. Very low severity burning historically in those forest types. Today it's more like 30 to 50%. So we're burning, mountainsides, we're burning all the forest down. And the Lake Tahoe Basin has a couple of really good examples of that kind of burning. And in chaparral, it's the reverse. Fire severity is actually going down because you're killing off the shrubs in the system. So in terms of post-fire influence, potential influences on debris flows, there's a lot of text here. I'm sorry, I'll try to distill it a little bit. But obviously, in both of these systems, debris flows are going to be most common, understand, replacing fire. But that was really pretty rare in these forests historically. All right, although, I mean, it was patchy. There obviously are places where you can load up trees on north-facing steep slopes where you probably did have pretty severe burning periodically. But under current trends, you're looking at large amounts of biomass loss on these systems. And the problem is that those forests don't have adaptations to quickly, like chaparral is adapted to come. Yeah, I mean, you've been in chaparral landscapes, I'm assuming, that have burned. If there's been a little bit of rain in the last year, 2 weeks later, there's resprouting already happening from the base. It's incredible. You do not see that in these fire regime group 1 forests. They require living trees with seed sources to reseed the site. And so if you burn an area of 1,000 acres and all the trees are dead, you're going to have things moving mile, 2 mile, 3 miles. You may never get trees in there again because it will fill with shrubs first, and it's likely today that it's going to burn again before you get. So I mean, we're seeing real permanent changes on landscapes. Yeah, so at any rate, et cetera, et cetera. And then I'll note that hardwoods are really important in the system, all right? And we should think about trying to actually restore forests, thinking about the future and incentivizing or creating situations for hardwoods actually to regenerate. Why? Because they resprout. Very, very quickly they get the soil covered up again, and actually they support a lot more faunal diversity as well. And then the bad, the sad story is, of course, that with these predicted probabilities of extreme storms in the future interacting with larger areas of forest loss, you guys are in a growth industry for sure in this room. And then in chaparral, it's the same thing, but for kind of different reasons. Chaparral always burns hot, and the hotter the chaparral system burns, the more you know that it was a healthy chaparral system. I mean, they're insanely hot at the surface, all right? And as a result, they kill all of the non-native seeds in the system, of which there aren't going to be any anyway because it was a completely closed canopy system and it hadn't burned for 30 or 40 or 50 years, all right? So the hotter it's burned, the more natural that system is. When you start getting patchy systems where grass is coming back right away, you know you have a big problem with respect to restoration. Where you do restoration, you need to think about what you restore, and it's important to think about, again, resprouting species rather than the ones that require seed casting and seed, because they take a lot longer to cover the soil surface. All right. Again, as I noted before, this is the same kind of situation where you have increased probability of extreme storms, and of course, Southern California has an outrageous. I mean, you guys have seen that classic graphic from who put out Dan Cahan and the one that shows the proportion of rainfall that comes in just a couple of storms across the U.S. Basically, once you get into coastal and central and Southern California, you're looking at all of your precip coming in 3 or 4 storms in a year. And so when it comes in, it hammers. And if it's a year after rain with all that earthquake going on, rising mountains, loose soil, I mean, there's it's obvious why that's kind of the center of the debris flow problem in the U.S. Anyway, so that's it. Can anyone tell me where that is? Got it. And so I visited that place in 1985. I did my field course for my geology field practicum with the University of Tübingen, and we stopped there on our way down the Rhone Valley and looked at, we didn't get a chance to see like one of those crazy debris flows, but that is geoporn. Wow. I mean, I checked it out recently because like, oh yeah, the Ilkhaben, I checked it out. And man, have you seen some of that stuff? There's like an hour-long video by a French guy, and you're just like, whoa, it's like a kid who won't stop throwing up, Just like, oh, okay, it's over. Whoa, here comes another one. It goes on for an hour. Anyway, okay, I'm done. Yeah.